Welcome to class 5 of stochastic control and communication. So last class we were talking about sequential decision making under uncertainty. I'll just do a quick recap. We were looking at problems which had the form of xk, which had which had a form of the system such that the system trajectory evolved as xk plus 1 is equal to fk, xk, uk and wk, where wk was random. UK was your control action, and XK was your state, current state. XK plus 1 was your future state, and FK is your system dynamics. Now, given the system dynamics, what we were expected to find was we were expected to find minimize expected value of the terminal cost and stage-wise cost you occur because of you taking action UK and going to some state XK. So stage-wise costs, which depends on XK, UK, and WK. Since there is randomness throughout this whole thing, we are minimizing the expected value of the cost. So we want to find U0 to UN minus 1, all these decisions. What we saw yesterday was finding out exact actions won't be possible because of the uncertainty in the system. Uh, Your states, anytime you take some action, you could end up at different states. So what you do is you try to come up with a strategy. That strategy was defined as mu. Um, so mu is a function which maps your states to actions. So states are basically set of xk's and actions are set of uk's. Right. So what this strategy tells is given a state xk, so if you observe that you're in state xk at time xk, then you take action uk. The strategy gives you the um, the the action basically. So this is a function. So instead of searching over real numbers and vectors, you're searching over functions, right? Okay. So this was what we discussed in last class. Today also I'll discuss. Okay, I'll first say what a policy is, and then I'll. So now you have these strategies, uh, mu0 to mu n minus 1, right? So mu0 to mu n minus 1 is basically um, just yeah, mu0 to mu n minus 1 is basically a sequence of your strategy functions, all those functions that you have taken a strategy. Now, strategy could be different for different time instances. Then they need not be the same function at each and every time instance. But this whole strategy altogether, the sequence of strategies altogether, is known as a policy. This policy is sometimes denoted as a pi. So when you see pi, it's basically a sequence of policies.
Will it be a sequence of policies or policy itself
Oh, so,
has many?
so sorry. Policy is a sequence of strategies. I'm sorry.
Yes, yes, okay.
Yeah. Policy. Thank you for correcting me. Policy is a sequence of strategies. So when I say from now on, when I say policy, what I mean is I have a sequence of strategies. All the strategies could be same. All those strategies could be deterministic. All the strategies could be random. They could be anything. I have not introduced different types of strategies yet, but basically policy would mean a sequence of strategies that you take at each time instance. Yeah, thank you for asking. Um, okay. So basically what happens is when you fix a policy, right, then um, okay, I'll do this step by step. So first you have x0, right? Now suppose you are undergoing policy mu0. If you undergo policy mu0, you know what x0 is. You apply x0 to the function mu0, you get u0. And then you get w0 from the noise. And then your x1 is realized as f of x0, u0, w0. But u0 is basically the function x0, mu naught x0, and w0, right? And similarly, now you have x1. You apply the strategy mu1, you get u1, and your system realizes a random variable w1. You get x2, which is f x1 u1 w1, which also can be written as fx mu1 x1 w1. So basically, this whole term, what what goes on here is you have the probability distribution of given a strategy, given a sequence of strategies, it gives you the probability distribution of xk plus 1 condition that you are on xk. So the policy determines how your trajectory evolves. So if suppose you fix a policy, say that your policy is okay, let's do it very simple. Let's instead of looking at policy, let's just look at one strategy. So suppose so it's basically one step. You're looking at one step. So now suppose you have one strategy, I have one strategy, right? My strategy is completely different to yours. Your strategy says that you want to do something, you want to do A if it's above B, if it's above 10, and you if the state is above 10, you want to do B if it is below 10. I say no, I want to do B if it is above 10 and A it's below 10. Then the next state, X1, would it would be highly different for you and me. And how does that difference come here is the probability distribution that your future state sees would be different to the probability distribution of the states that my strategy sees. Right. So, and I'm talking in probability distributions here in for the future states because there is the noise term W1. If there was no noise term, then given a strategy, you would exactly know what your next state is. But since there is noise, disturbance here, and with some probability you can go to different state and with some probability you can go to different state, you don't know what state you will go to. So what you get is a probability distribution on all the states, depending on what your noise is.
So, I mean, I could not understand the meaning of this term here. The probability of mu naught to mu k. So, is this a joint probability of?
No,
Uh,
no, 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 no. No. So this probability is a conditional probability on just the next state.
so, what this? I mean, mu naught till mu k in
Yeah,
the subscript is. I mean,
this mu naught till mu k in the subscript here just defines that this probability distribution is if you apply this sequence of policies to your system. If I check, if that is what I was giving as example, is that if you have a different strategy, I have a different strategy, then the probability that you go to state say x2 or x1 would vary. Like you have a different strategy, you say I'll use different strategy, I say I'll have a different strategy. Okay, I'll how do I tell you?
uh,
It's not clear right yet.
does it mean that I'm the does this mean that a policy is given and which has got these many strategies, say from mu naught to mu k,
Mm-hmm.
and under this policy and which has so many strategies,
Mm-hmm.
what is the probability of moving to the state xk plus 1 and given xk?
Yes. What is the probability that you go to x2, the xk plus 1, given you are at xk? So, most probably today, by the end of the class, I'll come up with an example. So, I'll introduce MDP and then I'll show you an example where this happens. So, if you take different actions, like different strategies or different policies, then what happens is sometimes if you take some policy, then your trajectory will be very much different than my trajectory if I take a different policy than you. If you both have different policies, then how your state evolves will be very different to how my state evolves. And that evolution of states is different because the probability distributions of the future states for you is different than the probability distribution of the future states that I have chosen. So
Yes, yes, yes.
so
Clear.
the subscript just tells that the subscript is just telling that changing policy would change your trajectory of the function. And to know how your trajectory is changing, we are giving a probability distribution on the future states based on the policy that you have chosen. I hope this is clear. Yeah, that is actually a good question. Okay, so one more thing is these first classes, these would be might be a little bit boring, and I'm not solving any problem. I'm just posing all the questions, but I'm doing this so that mathematically, as you have asked the question, what does the subscript mean here? What does the state mean? Where does the randomness come in? These are the things basically where people actually get confused here. So in stochastic control in reinforcement learning, what happens is the concept is clear. Like, okay, you're trying to learn something, you're trying to control something, you're trying to make optimal decisions on something. But what is it that you're trying to control and what effects it has on the system? Those things people uh, get confused in. So first, I just want to make the basics clear, and then afterwards, basics in the sense the notations and all the mathematical models clear, and then I'll go into solving problems and all. Because if I directly go into solving problems, it will be interesting, but it's counterproductive. So once you know the mathematical model to everything, then solving problem would be more interesting. Well, that's okay. So if you want the other way around, I can do it. But so yeah. So this sometimes we'll denote it as P pi xk plus one condition on xk. So yesterday we saw this whole thing as a stochastic control formulation. So in the same way, you can have an MDP formulation. MDP formulation also is the same thing as the stochastic uh, control formulation, where you have xk plus 1 is equal to f of xk, uk, and wk. Okay, is there background noise that's disturbing you guys? Is there a background noise that? Hello, am I audible?
Yes, yes, you are audible.
But is there a background noise that is disturbing?
Uh, no, 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 not much. You are clearly audible. I can hear
Okay,
you clearly.
okay, shit. Let me know if the background noise is more disturbing and then shift my range. So, um, yeah. So last time what we saw was FK was your dynamics, and the dynamics were given. But what if the dynamics are also not known, right? If they're not known, then we go into the formulation of MDP. MDP is same type of formulation where you have S, a state space. Uh, for now, we'll assume the state space to be finite, but you can have MDPs where the state space is infinite. A, this is your action space, or uh, your action space also will assume to be finite. So action space basically tells you that the set of all the actions all the controls you can take. So these are basically set of all U, U1s, U2s, U3s, and all. Yeah. And then you have RTS comma A. This is basically a reward that you get. Uh, at time t, reward you get at time t if you are in state A when action A is chosen. So if you choose action A when you're in state S at time t, then you get reward RTS comma I. Okay. Mm, and so there is this transition probability. Transition probability where you have probability at time t of the next state conditioned on the present state and the action you are. So this would give you the probability of the state being the dot at time t plus 1. So this is your action at t at time t. This is your state at time t. And okay, so um, people also get confused in two of these things also. So what happens is in stochastic control, what we do is we formulate problems as minimization problems in control, where you have certain cost to states and all, and being in a state is costly, and applying control you incur some cost. So all those comes under cost, and you want to minimize the cost. But in the setting of reinforcement learning and all, people assign rewards instead of cost, and they try to maximize the rewards. But philosophically, both of them have the same uh, structure. Like they both are similar in the sense, all the solutions that you want to apply, the method of solutions, like how do you get the optimal solution, all those methods, the same methods could be applied to stochastic control, the same methods could be applied to MDP, the same methods could be applied to the reinforcement learning setup. I hope this is clear. So in stochastic control, you're minimizing cost. In MDP, you are maximizing your reward that you have gotten for each state. So you are maximizing expected reward. This is your nth state reward plus equal to 0 to n minus 1, rt, st, comma a. St is your state at time t, and at is your action at time t. Here I could have, yeah, just written, but I've written it here. So yeah. Okay, so yeah. Now the similarity between these two, knowing the dynamics and not knowing the dynamics, comes from. So basically in MDP you have this probability of J conditioned on xk comma uk. So now I'm switching from, so when I'm in MDP setting, I'm using T as my time domain. And when I'm in stochastic control, I'm using K as my time domain. So basically, switching between both of these, you're trying to find the probability of next state being J, condition that your current state is xk and your action is uk, is basically equal to saying that probability of your function dynamics fk. If you know your fk, then you have xk, uk, wk is equal to j conditioned on xk and uk. These both are the same thing. Right. Here, this probability is over the randomness of wk. You know what xk and uk are because they're given, conditioned on you know what xk and uk are. So if you know the dynamics also, you can find the transition probabilities. So uh, the whole setup of stochastic control could be formulated as an MDP also. Okay, so I hope that is clear. Okay, now coming back to the MDP setting, similar. analogy to the stochastic control, we had strategies such as mu case. Here we have DTs, decision rules, which is similar to what mu k is. So you take, it is a function which maps from state space to your action space, right? Yeah. And now here also a policy is same denoted by your D0, D1 to DT, your decision rules at each time instance. They're both basically the same. You can interchange mu t and D0, but just because, so if you read an MDP book, you will find them using this notation. You will find them maximizing expected rewards. If you read a stochastic control book, you will find they are minimizing an expected cost. Uh, yeah, but they both can be interchanged because you have this, in one you know the dynamics, in one you don't know the dynamics of the transition probabilities. If you know the dynamics, you can go to transition probabilities. If you know the transition probabilities, you can somehow come up with dynamic system dynamics, but there are some assumptions that you need to. So this way is easy, but this way you need some assumptions. You need Markovity and all that. Will go, will come, we'll deal with it when it comes up. Okay, so yeah, so I'll end this here now. Yeah.
So what are these notations, dt and pi here?
Okay, so DT is similar to mu k. Mu k was a strategy that were discussing just now, stochastic, in stochastic control. DT is also function. DT is a function. I will call DT as decision rule. Decision rule. This is also function which takes states and maps to um, your action space. So DT basically takes xt and gives you at in this setting. So yeah, and
Yes.
pi is the same there and here also. So pi is basically a sequence of decision rules at each time. So pi is a policy. Policy would be the same. Your sequential decision making. So sequential decision rules is your policy. Their sequential strategies policy. So that pi denotation is same in both the cases.
Yes, yes.
Okay. So now we'll see some types of policies. Uh, yeah. So okay. So first, your decision dt is something which maps states to A. Now, uh, yeah, s- your decision rule is Markovian if your decision is just based on state at time t, right? And nothing else, nothing from the history. If your decision is just based on your current state xt and nothing else, then your decision rule is Markovian rule. And if all your decision rules are Markovian, then your whole policy is Markovian policy. Okay. Yeah. So first, just before describing all this, I'll tell you, I have to denote what history means. Right. So history HT is basically a sequence of all the values that you have taken till time t, and you have memory of it. So suppose you're at state S0, you take action A0, then you go to S1, you have A1, and so on. You are at T minus one, you're at state S1, ST minus one, you take AT minus one, you go to ST. This whole sequence, you know this sequence because you're currently at T. So this whole sequence is known as HT, and every term here is known. Hence, it's known as history. So HT is basically a vector of all the previous decisions and all the previous states. So capital HT is set of all histories. Now, set of all histories would be just Cartesian product of state, action, so on, state, action, state. This is for your zeroth, these two. This is for your first, and this is for your p minus 1. And then you just know the teeth state, you have not yet taken the action. So basically what is happening is at each step you're increasing in dimension. So your h0 would just be s, your h1. So h0 is set of histories at time 0. H1 would be set of histories at time 1. At time 1 you have already taken an action, so it will be more than h0. So you'll have 2, it will be 2 dimensional. And then h2 set of histories at mm, uh, okay at time 2, it will be s a s no a s. So these two are for 0, these two are for 1, and this is for 2. Yeah. So it will keep on increasing. Okay. So now, yeah, here your decision rule, if it just mapped your state to action, then we call it Markovian, right? If your decision rule maps these histories to an action, then it is known as a history dependent decision rule. Okay. Both of these decision rules are clear, I think. So now I'll introduce set of policies M. Pi M is set of Markovian policies. So basically what this has is, so pi means you'll have a sequence of d0, d1, d2, and so dn minus 1. Now, if all of these decisions are Markovian, then pi m is basically set of Markovian policies. And similarly, pi h is set of history dependent policies. Okay, so one observation that you can see here is um, Markovian is basically a special kind of history dependent policy, but instead of depending on the entire history, it just depends on the uh, last. So it ignores the whole history behind and just depends on the last vector, the latest information that you have. Uh, is that clear? So what I'm trying to say is, uh, your all Markovian policies is a subset of your all history dependent policies. So your set of Markovian policies is a special case of your history dependent policies, because in the history dependent policies, you just ignore all the previous history and take the latest information that you have and take your action based on it.
Yes, so Markovian means the latest history and without considering history much. Is
Yeah,
it?
yeah. Yes. Latest in the sense just immediately, just one history. You don't consider the whole string of uh, vectors that you have from time 0. That is Markov.
Yes.
And history dependent means you take all the histories. So while solving MDPs, the whole point of MDP, Markov decision processes, is that you're working under the assumption that you're Markovian. So your system is Markovian, and so that makes it a lot easier. And um, uh, this subset equation that we have written, the policies set of policies of Markovian is subset of set of policies of history dependent. What this means is, under some assumptions, and some assumptions we'll discuss this later, you can show that the optimal uh, policy that you can get, even if you search among history dependent policies, sometimes under good assumptions, what happens is it falls under Markovian policy. You don't need to go look at history dependent policies at all, right? So those kinds of things come up, but that we'll discuss later. So right now I'm just saying, okay, I'm giving the definition of Markovian policies, history dependent policies, And I'm stating that Markovan policy is a special case of history-dependent policy. Okay. Uh, there is one more kind of policy, that is uh, stationary policy. So uh, phi equal to d0 to dn minus 1. This is this is a stationary policy if these are independent of time. So basically, you have the same strategy okay, let's call it ds at each time instant. If you have the same uh, decision rule at each time instance, then you have then that policy is known as a stationary policy. Okay, so one important uh, point that I want to state is that people get confused is uh, this does not mean I am taking the same action every time. It just means that my decision rule is same at each time instant. My decision rule is same does not imply that I take the same action every time. Because I have some randomness in the system, and because of the randomness, I can change my state at each time. So once I change my state, I change the action, but the decision rule remains same. I hope that is clear. And similarly, I'll denote pi s as the set of stationary policy. Okay, so uh, I think this is not obvious, but I hope you see that your stationary policy is a special class of Markovan policy, is a special class of history pi s, pi h. I hope this makes sense.
Yes.
Yeah. Okay. Yeah.
So stationary
Yeah.
policy means that on every timestamp the strategy is same, or it could be like, say, on every timestamp. I can have a different policy, but different strategy, but that strategy is random.
Um, okay. You're correct in both the same. So when you say strategy remains same, it remains same throughout. And I believe what you're asking is my strategy could be random. Yeah, strategy could be individually random. That is correct.
Could be individually random, but same across all the timestamps, or it may differ at different timestamps.
No, no. Stationary means it's same across all the timestamps, but individually it could be random.
Okay, okay, yes, it's clear. Yeah.
It is same across all the timestamps. Same across all the timestamps. The strategy, the decision rule or the strategy is same across all timestamps. Your actions, like the decision that you take at that time instant, could be something else because you're a different state, or because of the randomness in the system, or because your decision rule itself is random. That could happen.
Okay,
So, actually, today this class will answer all these questions that you're having. That you're having. So I have defined three types of policies, right? One is Markovian, one is history dependent, one is stationary. Next is randomized policy. This is what I think you were asking. I'm not sure. This randomized policy. So randomized policy basically has nothing to do with the above three, but what it does is, so the decision rule is random, right? So now instead of so till now what did we have? You had DTST, give a state and you'll give an action, right? So instead of an action, you'll have a probability distribution over the actions. Okay, so basically what this means is, suppose you have two states, one, two, right? You have two actions. Say, with if you're a state one, if you take action one, you're at one. If you take action two, you go to, okay, actions may be ABL, right? So, and this example I've thought of introducing it later, but I'll do it now. Okay, so you have two states, right? S equal to state one, two. You have two actions, A comma B. If you take A action, you're at the same state. If you take B action, then you switch. But yeah, suppose you do this, right? Now, your one decision rule could be that suppose you prefer state one, you don't want to go to state two. So your decision could be that if I'm at one, then choose A. If I'm at two, choose B. Then what would happen is if you are at 2 you would come to 1, if you are at 1 you would come to 1, and you'd always like uh, if you run this decision most of the time, what will happen is you'll stay at 1 throughout the thing, and state 1 is more preferable than state 2. Preferable, that will come later, how that all is defined, but this is what happens now. So this is basically strategy deterministic strategy. So each strategies or each decision rules are deterministic. Now, if I say D1, you choose A with probability 2 by 3, you choose B with probability 1 by 3. D2, you choose A with probability, say, 1 by 4, and you choose B with probability 3 by 4. Now, these type of decision rules are known as randomized decision rules. You understood the difference between both of them, right? So, yeah, right out.
Yes. So, yeah. So what this yeah, P of A here is probability stands for the probability or for the power set kind of thing.
No, 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 no. This stands for the uh, set of probability distributions over the actions. So my A set is set of A comma B. Now, when I denote this, it means that all the probability distributions over this set. So all the probability distributions over this set would be 0 comma 1 cross 0 comma 1. You have to choose, and you have the extra constraint that A comma B belongs to this, and A plus B equal to 1, this set.
Okay, okay, yeah.
Where okay, I should not have written A here, maybe something else, XY, uh, XY. And what X denotes is the probability you choose A, Y denotes the probability you choose B. Okay, I hope, yeah, okay. Mm, uh, Now here, I think you will see that the deterministic policy is basically a special case of randomized policy, right? Because you can just choose uh, this above uh, rule. I can write D1 is equal to A with probability 0 and B with probability 1. Sorry, with A with probability 1 and B with probability 0. D2 is equal to A with probability 0 and B with probability 1. So all your deterministic policies are also a part of your randomized policies. So basically, if you have set of randomized policies, a subset to it is set of deterministic policies. So set of deterministic policies is subset of set of randomized policies. Okay. So yeah. Okay, I was about to write this down. Okay, I was about to write this down. You asked the question. Okay, I'll just do it down here. So PA here means the set of distributions on the set of actions. Okay, and um, yeah. So this whole term, instead of writing it like this, what we'll do is we'll write this as Q dt st a So this is your probability of choosing action AT at ST under the randomized decision rule DT. So if DT is a randomized decision rule, I'll denote it with Q. The subscript will denote my randomized decision rule that I'm following. AT is the probability that you choose action AT at ST. And yeah, so the constraints that this will have is Q DT ST AT is greater than or equal to 0, and summation over all actions, this Q DT ST A, this will be 1, because you have to take some action. You can't just skip all your actions. So now one thing you'll say is this randomized policy has nothing to do with the history or anything. It's just saying how your decision rules are. So basically, you can come up with many more number of sets such that you have SR, which is set of stationary randomized policies, and you can come up with pi MR, set of Markovian randomized policies. And you have pi HR, set of history dependent randomized policies. And we have already seen that deterministic policy is a special case of randomized policy. Yeah, so in the same way, you can go from, you can define any deterministic policy as this. So where so if you want to write it more clearly, suppose DT is a deterministic policy. This is a deterministic policy, right? So DTST equal to AT. Now, how do you write it as a randomized policy? Is QT DT ST AT is equal to 1 if A equal to AT. So suppose this is A, and 0 if A is not equal to. Yeah. Okay. So I'll quickly note down all the observations that we made. So all stationary policies are a special form of Markovian policies, are special form of history-dependent policies. All history-dependent policies come under all history-dependent randomized policies. Similarly, all Markov proper policies are Markov randomized, stationary, stationary randomized, and stationary randomized, Markov randomized, history rank. So these are something which you keep in the back of your mind, but it will not be using this that much. Um, uh, but why do we need this all dependencies? We want to come up with policies that are easy to handle. So Markovian policies are easy to handle, right? So you want to see under what conditions does just finding optimal policy in this Markov based Markov policies would also be optimal for your whole bigger policy space of pi HR. So you want to know that under these assumptions it is the optimal in both of the sets are the same, then you don't need to search pi HR, which is a bigger set. you can just search in Marco policy and say that, yeah, it is optimal in all. So because we want to make those claims, it's better to know what types of policies am I searching in, and what types of policies are there which are bigger than the policies that I'm searching in. So today's class, so I'll end with giving a very small example on MDP. So suppose I have two states, S1 and S2. Okay. And I have actions, say A11, A11. Okay. A12, sorry, just a So I have two states. So basically I have two states, S1 and S2. S1 has two actions, A11 and A12. S2 has one action, A21. If I choose A11 in S11, then it goes to S2 with probability 0.5. It goes to S1 with probability 0.5. Yeah. If I choose A1 to, okay, so this arrow is, so this is A12 and this is A21. Okay. So basically I have two states. Uh, S1 and S2 are my two states. When I'm at S1, I can take two actions, A11, A12. When I'm at S2, I can take only one action, A21. A11 is basically I again go to state S1 with probability 1. A12, I go to S1 with probability half. I go to S2 with probability. No, no, no. Sorry. A11, I go to S1 with probability half. Uh, I go to S2 with probability half. Um, A12, I go to S2 with probability 1. And A21, I stay at S2 with probability 1. Okay. And rewards is choosing A11 at S1 gives me reward 5 anywhere I go. Choosing A12 at S1 gives me 10 reward. Choosing A21 at S2 gives me -1 reward. So these are my rewards. I want to maximize my reward. So I'll add on the rewards also here. So here I get reward 10 and 1. One is probability with which this goes. And here I have 5 and 0.5. Here I have 5.5, and here I have -1, 1. So basically, I don't want to go to S2, because if I go to S2, then I can't come to S1. And I always have to take decision A21, which will incur me a reward of -1. I want to maximize my reward. So I want to stay at S1. But if I want to stay at S1, then I can't indefinitely stay at S1, because I can't choose A12 because I'll go to S2. I can choose A11, but I don't know, because there is some randomness with some 0.5. I can always go to S2 directly. So this is your whole setup. Like there is some randomness. You know what to do. You know the optimal thing is to stay at S1, but you might take an action which might not lead to the optimal solution. So we are not worried about optimal policies right now. We are just worried about different types of policies that you can see on this. Okay, is the problem setup clear? Okay, this I'm not equating it to. I'm not calling this an example because it's not a real life problem that I'm mapping into this problem. I'm just uh, placing numbers to the states and actions. I'm not doing anything else. Just taking an states and actions. Maybe in the next class, I'll come up with a real example and then model it as an MDP and then attach rewards to it so that it will be more clear. But for today, because I'm discussing on what different policies you can see on some MDP, I'm just putting numbers to some actions and states and then coming up with policies. That's it. I'm not doing any optimality right now, just different types of policies. Okay, so what we'll do is we'll first fix n equal to 2. So basically, you don't have to worry about the whole um, your whole trajectory. You just need to worry about two states, right? Uh, First, we have deterministic Markov policy. So your pi md. So at time 0, d0 md introducing because this I want to make sure that the decision that you're taking is Markov deterministic. S1 you take A11, D0 MD S2 is you take A21. Okay. And at time 1, you have D1 MD S1 A12 and D1 MD S2 A21. So this is one example of your deterministic Markov policy. So why is it deterministic? Because you give a state, you get an action, and for zeroth time, for all the states, you have an action. So this is basically the function that you want to map to. And at time 1, you have an action. So your pi md that you have chosen is basically d0 comma d1. And this d0 and d1 I have defined here. Right. Now, if you want randomized Markov policy or pi mr, then basically you can say that at decision at time 0, you have q d0. Now you have randomized Markov, state S1, action A11 you take with probability 0.7, and same S1 A12 you take with zero point 0.3. Right. So if you define something like this, then basically you're defining randomized Markov policies. Okay. Third is your history dependent policy. So here you'll not see much of a history dependent policy because if you are at state S1, then you know that you are at state S1, right? You can't go from state S2 to S1 because the dynamics of this problem, the history dependent policy would be just if S1, this implies whole history was in S1. So because your whole history was in S1, you know all the pairs of um, uh, all the states and all the actions that you have taken till now to go to be at S1. That pair is basically all your states are S1, S1, and all your actions are A11, A11. Because if you take A12, then with probability 1, you go to state S2. So you have not taken A12, you have taken A11. And if S2, then you will basically boil it down to you are in S1, you take action A11, previous state, you're in S1, you have taken A12, you were in S2 and you have taken A21. It'll boil down to just what previous state you were in. If you know what previous state you were in, then you know the whole history. So basically, because you have this Markovity property from this MDP diagram that we have, so your all history dependent policies would be your all Markov policies because your states are such a way such that they depend just on your previous state and not the whole future. Okay, so maybe yeah, I'll stop here today. So in the same way, you can come up with all different policies which are stationary, which are I think I've covered most of them. I've covered deterministic Markov, randomized Markov, history dependent. Um, yeah. If you cover these three, I think you have covered most of them. Next class, I think uh, I'll I'll go to principle of optimalities. Now in this class we have defined all the types of policies that you can see. So next class we'll see, okay, how do I say which policy is better than which policy? How do I say, um, uh, uh, how do I come up with saying that, okay, this policy is better than that policy? And if I know a way of comparing two policies, then how do I say that, uh, or some properties of what the optimal policy would show? That we'll see next class. You okay? I'll stop the recording.
So, can you suggest some book or some tutorial?